Modeling the action of forces. In the ongoing provided picture, the common type of forces application on mechanical system for analysis in two-dimensional were shown. Each example shows the force exerted on the body to be isolated by the body to be removed. Newton's third law, which notes the existence of an equal and opposite reaction to every action, must be carefully observed. The force exerted on the body in question by a contacting or supporting member is always in the sense to oppose the movement of isolated body, which would occur if the contacting or supporting body were removed. At first, we are going to describe the modeling the action of forces in two-dimensional analysis with the cable, flexible cable, bed, and rope. Consider this picture for more description. As we shown in the picture, the first one is flexible cable, belt, chain, or rope. This example depicts the action of a flexible cable, belt, rope, or chain on the body to which is attached. Because of its flexibility, a rope or a cable is unable to offer any resistance to bending, shear, or compression, and therefore exerts only a tension force in the direction tangent to the cable at its point of attachment, as shown in this picture here. The force exerted by the cable on the body to which it is attached is always away from the body, also shown here and here. When the tension T is large compared with the weight of the cable, we may assume that the cable forms a straight line. This picture. So right weight of the cable is negligible. When the cable weight is not negligible compared with its tension, the sag of the cable becomes important and the tension in the cable changes direction and magnitude along its length. Two types of tension. The type 1, the weight is cable is negligible, and the second one, weight of the cable is not negligible. The difference is to the theta and the direction of T on the structure. When the smooth surface of two bodies are in contact, there is another example of free body diagram. Consider this picture. Example 2 shows the contact point in smooth surfaces. This example shows the smooth surface of two bodies are in contact. As in this example, the force exerted by one on another is normal to the tangent to the surface and is compressive. Although no actual surfaces are perfectly smooth, we can assume these to be for practical purposes in many instances. The force is normal is in the direction of the contact point, and also the opposite force is on the ground. The next example is about the roof surface. When making surface of contacting bodies as roof, 3. Contact bodies. The force of contact is not necessarily normal to the tangent to the surface, but may be resolved into tangential or frictional component F and normal component N. As shown in this picture, we have two forces, normal component and tangential component F, as well as normal component N, and the resultant of R. Another example in the free body diagram context are ruler support. For ruler support, example 4 illustrate a number of forms of mechanical support which effectively eliminate tangential friction force. In these cases, the net reaction is normal to the supporting surface because the structure cannot resist in the horizontal force applied on them. We have only normal forces on the structures. As shown here, different types of ruler support are shown and may be used in problem. The next example is the freely sliding guide. Freely sliding guide. Example 5 shows the action of a smooth guide on the bodies. Its supports 3. There cannot be resistance parallel to the guide as shown here. This structure cannot resist showing resistance on applying force in horizontal direction, so the only reaction is in the normal direction. The next free body diagram type of contact and force origin is the pin connection. In the next page, this example shows the pin connection 6. Example 6 illustrates the action of pin connection. Such a connection can support force in any direction normal to the axis of the pin. We usually represent this action in terms of two rectangular components as shown here, and the resultant of R. The correct sense of this component in a specific problem depends on how the member is loaded. When not otherwise initially known, the sense is arbitrarily assigned and equilibrium equations are then written. If the solution of this equation yields a positive algebraic sign for the force component, the assigned sense is correct. A negative sign indicates that the sense is opposite to the initially assigned. If the joint is free to turn about the pin, the free to turn P not free to tear. The connection can support only the force R. If the joint is not free to tear, the connection can also support a resistant couple M as shown in the free body diagram for this connection. The sense of M is arbitrarily shown here, but the true sense depends on how the member is loaded. The next example is built-in or fixed support. Example 7 shows the built-in or fixed support. Built-in or Example 7 shows the resultants of the rather complex distribution or force over the cross-section of a slender bar or beam at a built-in or fixed support as shown here. Built-in and fixed welded support. The sense of the reaction F and V and the bending couple M in a given problem depends of course on how the member is loaded. And the next example is the gravitational attraction. Example A. This example shows the gravitational attraction. Gravitational attraction can be different. One of the most common forces is that due to gravitational attraction. This force affects all elements of mass in a body and is therefore distributed throughout it. The resultant of the gravitational force on all elements is the weight, for example, as shown in the picture here, on G, which passes through the center of mass G and is directed toward the center of the Earth for Earth-bound structure. The location of G is frequently obvious from the geometry of the body, particularly where there is symmetry. When the location is not readily apparent, it must be determined by experiment or calculations. Similar remarks apply to remote action of magnetic and electric, gravitational magnetic or electric fields. Electric field forces. These forces of remote action have the same overall effect on a rigid body as force of equal magnitude and direction applied by the direct external contact. The last example in this chapter that's shown is a spring action. Consider this picture. A spring action. This example illustrates the action of a linear elastic spring and of a nonlinear spring with either hardening or softening characteristics. Two different springs show behavior of two different springs shown here. The forces exerted by a linear spring in tension or compression is given by this formula, F equal to Kx linear where K is the stiffness of the spring and X is its deformation measured from the neutral or undeformed position, as shown here. These pictures are not free body diagrams but are merely elements used to construct free body diagrams. Study these 9 conditions and identify them in the problem board so that you can draw the correct free body diagrams for any systems. Construction of a free body diagram have 4 steps that will be described in the next video.